Okay, gonna make one more try at this. Was too tired last night, kept yawning. So here we go. The graph lab, things you want to know. Lab design, basically there's two pieces to the graph. There's the implementation of a node of the graph, which also stores links to other nodes, and then there's the graph object itself. So those are the interfaces are inode and igraph. And the implementations are node and graph. I'll show you this in Eclipse. You want to implement node first, then graph. There's 3 sets of JUnit tests: basic, advanced, and utilities. The basic tests will test out all of this stuff that you need to implement. You may need hash code and equals for node if you're going to put node into a hash table or hash set. I'll talk about that. That's probably going to be in a separate lecture, or I'll just do it in class. There's input files for reading a graph. I'll talk a little about those. And then GraphViz, I'll show you what GraphViz looks like. So we got to jump over to Eclipse here. So inode and igraph, your starter package, you won't have a default package, examples, or the solution, and you also won't have doc or old. You will have these files here. I'll show you what those are. And you'll have this graphs package with this code in it. Here's inode, here's igraph. These are the classes that you're working with. So if we look at inode, I should rephrase that. These are the interfaces you're working with. These are all the methods that a node needs to have. You'll notice this is an interface, which in Java means it's sort of like a base class, but it doesn't have any code in it. It only has method declarations. So all the methods are just the visibility modifier, the return type, the method name, and then whatever parameters there might be, and then a semicolon. There's no method body for any of these. These are just, they're all what are called abstract methods. They don't have bodies. So this inode and this igraph, these are defining what methods a node and a graph need to have. And so if you look at inode, you've got getName, you've got getNeighbors, which returns a collection of inodes. A collection can be basically a list or any of its derived types, or a set or any of its derived types. So, you know, queue, linked list, array list, hash set, tree set, things like that. Can't be a map. The reason being, a map has both keys and values. Could be just the keys of a map or just the values of a map. Those are both collections, but a map itself is not a collection because it has both keys and values. So neighbors, if you say get neighbors of a node, it's going to give you like a collection of all the nodes that are neighbors of that node. Add directed edge. So we can say, I want you to add a directed edge to this node with this weight. We can add remove undirected edges. We can remove directed edges, and there should be one other here. Yeah, there we go. Add directed edges. So we can add and remove directed and undirected edges. And we can get the weight to a particular node. This should throw an exception, such as an illegal state exception if there's no connection to that node. And then has edge, if you give it another node, it's going to say true or false, do you have an edge to that node? So that's what we've got going on for the inode. And then when you implement this, you're not going to implement it in this file. You're going to implement it here in this node. So you see public class node implements inode. And so all the methods in here are overridden. But as you can see, we've once again just got this default method body that just throws an exception with everything. And so you're going to implement all of this in here. Now, igraph, this is made up of inodes. So first we've got the breadth first search, depth first search, and Dijkstra's methods. Don't implement those first. Implement those last. I should probably change the order in which things are listed here. Get or create node. So you give it a name. All the nodes have a name, which is a string like A, B, C, D, or node 1, node 2, or 1, 2, 3, or whatever. But it's some string. So if I say get or create the node, well, if a node with this name already exists, it's just going to return it. If it doesn't exist, it's going to create it, store it, and then return it. I'll give you a hint. You probably want a map inside your igraph class that stores a collection of all of these nodes mapped with their names as the keys. We've got contains node, so it'll tell you true or false, do you contain something with this name. Get all nodes, this just returns a collection of all the nodes. These methods here, to dot file and to weighted dot file, these actually take the graph and put it into a special format that you can view it with what's called GraphViz, which is a graph visualization toolkit that I think comes out of AT&T Bell Labs or something like that. It's a really, really awesome tool. So you don't have to write these methods. These are actually going to be written for you. So that's all the stuff you've got in iGraph. If you look at Graph, the actual implementation of that, so we've got public class Graph, implements iGraph. It's got all these methods in here, breadth first search, depth first search, and Dijkstra. And then do those last, and do things like get or create node and contains node and things like that first. And if you look down here at the bottom, you'll notice you've got two methods. They're actually sort of showing up here. Create undirected graph from adjacency list and create undirected weighted graph from edge list. These are sort of like constructors, but they're called static factories. I'll explain that in a second. And then here's this two dot file and two weighted dot file. These are creating what are called dot files. So these four methods, these two static factory methods, and these two dot file and two weighted dot file methods, these work together. Let me show you what these are doing. So create undirected graph from adjacency list. This is just saying, okay, I want to read a file. We're actually setting it to an input stream, but of course, as we found out in the spam filter lab, input streams can read from files. Here's what the format would look like. So it would look like this. And so this is just telling us, okay, there's a connection from A to B, D, E, G, H, and there's a connection from B to C, D, and there's a connection from C to D, E, G, H, and so on. So it's just sort of telling us, here's all the nodes, here's all the things they have edges to. And you only have to show the edge in one direction in this format. So like, you know, we know that H has a connection to A, and H also has a connection to C, but we're not actually showing that H has any other connections because you only have to show the edge once. And so when you call your method to create an undirected graph from an adjacency list, it's going to read this file and then create all of the necessary components using your methods, get or create node, and create edge, or create, I forget what it's called, whatever it is in inode that creates an edge. And that's going to produce what's called a dot file. If we open the dot file, well, I should rephrase that. There's a couple things happening. There's the static factory itself, which just returns a graph. And just a word about the static factory. If you remember in Java, a constructor must have exactly the same name as the class it's located in, and it can either throw an exception if it crashes, or it has to return a new, freshly created instance. A static factory is a little bit different. It's just a static method. We call it a static factory because it has a specific purpose. If it's in the graph class and it returns a graph, and it kind of operates like a constructor, but it can have a much more descriptive name, and it can actually return cached instances or subtypes or kind of whatever it wants. And so all this is going to do is sort of read through this file, and parse all that text, and then produce a graph. So it's going to create a graph, and it's going to keep adding, get or create every node that it sees, and then add these undirected edges to its peers and stuff like that. So it's just basically going to go ahead and create the graph, and at the very end it returns the graph. So it operates very much like a constructor. Now you might ask, well, why didn't we just have two constructors? Why do we have two static factory methods instead? Funny you should ask. I can tell you. You'll notice that this static factory returns a graph, takes an input stream, but it's expecting to read an undirected graph that's also unweighted. If you look at this static factory method, it also wants to read an input stream and return a graph, but this one wants something that's undirected and also weighted. So we want to be able to have two constructors that both read an input stream. That wouldn't work in regular Java if you've got two methods that have the same name, which constructors have to, and the same type of parameters. In fact, that's the same method. That's not allowed. So we actually have to use static factories here to have two methods that both read, or two constructor-like methods that both read an input stream. There's other uses for static factories. If you notice, the capital I integer wrapper type doesn't really have a constructor. It has this static value of method where you give it a primitive int and it gives you back the big I wrapper type integer. That's because those wrapper type integers, they're immutable. Like if you have the integer, 17, that's going to be an object that has the number 17 inside it. You don't need more than one instance of 17. So if you use a constructor, every time you create one, you have to actually create a new one. If you use a static factory method, what it can actually do is maintain its own internal cache, basically some sort of a map. And when you ask for 17, it'll look it up and say, hey, do I already have the object that corresponds to the primitive int 17? If I do, let me just go ahead and return that. And then if not, I'll go ahead and create it. Another good example of this is the wrapper types for Boolean, true and false. You only need one instance of true and one instance of false. It doesn't make sense to create a new one every time. So there's other uses for static factory methods. But in this case, we're just interested in basically having two things that both read the same type, but act like constructors. Now, once you've read in, sort of an undirected graph that's unweighted, or an undirected graph that's weighted. I didn't do anything for reading directed graphs, but we certainly could add that in a future version. We also have these two dot file methods, and so these are instance methods, not static methods. You say the name of the graph you'd like to generate. The name doesn't actually matter as long as it's a string and starts with a letter rather than, basically follows standard identifier naming rules. This is going to go ahead and create a file in a special format called dot. So if you, for example, read in this adjacency list, it would then produce this. I'm going to open it with a text editor first, so you can see it's got graph, G1's the name, it's got these curly braces, and then it's got stuff in this kind of weird format. This is describing all the edges. That's all fine and well, but if you open it with, where are you, GraphViz? Well, I have it set so that the system editor will get it. It actually will visualize it in this format. Now, on the Mac, you'll have to just install GraphViz and then do, when you open it, you'll probably have to do open with, and then you'll have to do other, and it'll sort of bring up this, well, eventually it'll bring it up. Okay, why don't we just sit here and watch the spinning wheel? Oh my gosh, really? We're going to sit here and watch the spinning wheel? There we go. It'll bring up your list of programs, and you'll have to go find GraphViz, which you will have installed, which will look like this. Now whenever you open dot files, it'll open them up with GraphViz, and you'll get this nice visualization of the graph that you kind of described in text. You get a good visual view of it now. On Windows, you'll have to download GraphViz, which is linked on the Moodle page, or you can go to the GraphViz download site. Unzip it, and then there's a gvedit in the bin folder. You'll have to find that, open it, and then have it come and open these files. I didn't spend a ton of time on it, but I didn't figure out any way to get, well, actually, if you do open with it might work as well on Windows if you do open with, but you need to find the program. I believe it's called gvedit is the one that you want. On the Windows side, there's a bunch of executables in that bin folder. So the one that's up on Moodle, it's called, you'll unzip it, it's called GraphViz. It has a bin folder in there. Bin stands for binary, which these are the executables, and there's something in there called gvedit. So if you open these files with that, you'll get this kind of view. On Windows, you might need to open it and then tell it to run to generate this or something. So you get these nice visualizations. And so for example, over here, this is the sort of the weighted version. So this is the other static factory methods. It's saying A and B have an edge with a weight of 6, and B and C have an edge with a weight of 7, and so on. And if we open that with GraphViz, we actually get kind of exactly what's described in here, but in a nice visualized format. And so you don't have to write the static factory method, and you don't have to write the two dot file methods for the weighted and the unweighted versions. That's actually all implemented for you. And nobody bothered with it last year, which is depressing. But if you want to try this out, it's actually a really, really cool tool, so you can check it out. And hopefully it'll make your life better and whatnot. Other things you need to know: graph test basics. So as you start implementing inode and igraph, or rather node and graph, and start with node first. For goodness sake, don't start with graph, because graph uses node, whereas node doesn't know anything about graph. Start with node first. You can start testing things with this JUnit file. So you can see node constructor, tests that you can create a node named A, and it asserts that A is the name, and 0 is the number of neighbors. When you create a fresh new node, it's going to have no neighbors. Undirected edges, you're going to create 2 nodes. You're going to add an undirected edge between them with the weight of 5, and it's going to assert that 5 is the weight from N1 to N2 and from N2 to N1. Now, a couple of notes of what's going on here. You'll notice that everything we're creating here is we've got the pointer as a reference. The reference type is inode, but the actual type is node. That's okay because node implements inode, so that means it's a subtype. So that definitely works. So anywhere here, the getWeight method is expecting an inode, so you can put in an inode or anything that's a subtype of inode. So this would actually work even if this were just node. So you check that out; it still compiles. But I'm going to stick with inode because that's usually what you want to do is use your base types instead of your derived types. So test add directed edge. It creates 2 nodes, adds a directed edge from between them, and then make sure that you have the edge in one direction but not the other. This is actually a really cool trick. We're asserting that 6 is the weight of the edge from 1 to 2, which makes sense because we said N1, you have a directed edge to N2 with a weight of 6, but that means that N2 should not have an edge back to N1. So we're trying to get the weight from N2 to N1. Remember, this should throw an exception. So if it throws an exception, we go to the exception handler, we do nothing, which means it'll look like this test case passed. If it doesn't throw an exception, this is a JUnit thing, which just says fail this test case right away. You should not have gotten to this point. So this is kind of a little trick for testing that a method throws an exception when it's supposed to. We've got more complicated examples and so on. And so most of the basic, really all the basic functionality of Graph and Node is tested out by Graph Test Basic. Now, breadth first search, depth first search, and Dijkstra's, those are tested in Graph Test Advanced. So test breadth first search, test depth first search. These actually aren't test cases so much as they create an undirected weighted graph from this test Dijkstra. I call it test Dijkstra because I originally wrote it for Dijkstra, but we're using it for all of them. I'll show you that graph in a second. Well, maybe I'll show you that graph now. Here's what it would look like using GraphViz. So it's sort of a big graph. It's weighted, and we're going to do traversal starting at A. And we're going to see what would a breadth first search and depth first search traversal looks like. Now, of course, with breadth first search and with depth first search, we know we have to do neighbors before neighbors or neighbors before neighbors, depending on which algorithm you're using. But there's no specification which neighbor. So, for example, if I'm doing breadth first search, I have to do F and B first before I can do K, G, and C. But I could do FB or I could do BF. It doesn't really matter. There's no specification for which one I should do first. So, given that that's the case, and we sort of have no idea what order we're doing things in, all this does is create the graph. It does a breadth first search from A. All it's doing is printing out the node. I'll explain what's happening here with this visit method in a second. And then it's just kind of failing. Not failing because it doesn't actually work, but failing to kind of remind you that what you have to do is actually look at what it prints and see if it's printing the right thing. And actually, if I make changes here, you won't actually get them. Same with depth first search. With Dijkstra's, it actually runs Dijkstra's to find the shortest path, and then it sort of creates a map out of the map that it gets back, and then just sort of asserts that the correct cost shows up for everything. So this you can actually just run like a regular test case. And in the future, what I'm going to do is set it up so that I can automatically generate a graph and then automatically generate this test case for the graph. I haven't actually done that yet. That would be really fun, but I really need to write lectures and grade, which is fun, but less fun than coding would be. So these are the more advanced tests. And then finally, we've got graph test utilities. This is actually testing out the 2 dot file methods. It's just kind of showing you how to use them. I have these failing as well because these are just main methods. These aren't actually testing anything. In that there's no assertions in here, so if you were to run this and it didn't throw an exception, you might assume that the method was fine, but the method may not be fine. What you actually have to do, sort of reading in g1.text and generating g1, you have to sort of look at it and make sure that it looks like it's doing the right thing. That's kind of the state of affairs that we're at here. So that's test basic, test advanced, test utility. The final thing is this node visitor. This is called a functor. It's just a one-method interface that has a visit with an inode. And so when you're doing a breadth first search or a depth first search, you're traversing the graph and visiting each node. But what you do when you visit the node is totally up to whoever's doing the breadth first or the depth first search. You don't want to define what they have to do when you're implementing breadth first search and depth first search. So if you note what in iGraph, what breadth first search and depth first search do, they tell you the name of a node to start at and a node visitor. Now the node visitor, this is just one of these little things here. It's some implementation of this interface. And so what does that mean? Well, that just means when I do a depth first search, you're going to give me an implementation of node visitor with this visit method to tell me what to do with each node. So for example, if you look at not graph test util, you sort of can't see the little screen recording thing. I have to keep moving around, but it's definitely there. Well, whatever, I'll get it from here. So if you look at, for example, graph test advanced, I'll go ahead and maximize this. We create a graph. We're sort of using the static factory method to read it from this test Dijkstra.txt file. Now we're saying, okay, I want you to do a breadth first search starting at the node named A, and here's this new node visitor. Now, this is what's called an anonymous inner class. We want to create a class that implements this, but we don't want to give it a name because it's just going to be created in this one instance and used one time. So we're saying new node visitor. Node visitor is an interface which you normally can't create implementations of, but this is a special chunk of code which is saying a new one of these, and then instead of having a semicolon or closed paren or something here, we actually have an open bracket, closed bracket, and then we're just sort of sticking in the body of the method that we would like to have this do, and all it's doing is printing out, you know, the name of the node. It's saying, okay, I've got an inode here, I'm just going to get its name, I'm just going to print out the name and say, hey, look, I'm visiting this node. And so you can kind of look through the printing and realize, oh, look at the order in which I've visited everything. And actually, you may want to do this. You may want to change this to BFS visiting node, and then this one to DFS visiting node, so you know, so you actually can differentiate in case all the printing kind of gets stuck together. And so we're kind of doing the same thing down here. This is actually much cooler than it looks. To be able to have this general way to do a breadth first and a depth first search. I tell you the name of the node to start at, and I give you the node visitor, and then your implementation doesn't have to worry about anything. All it's going to do when it gets to each node for the first time is it's just going to call the visit method. So, you know, you've got this instance of node visitor. From your perspective, where are you, graph? Fine, I'll get it this way. Yeah, breadth first search. So from your perspective, you've got this node visitor v, and you know it has a visit method. So the first time you get to a node, you just do v.visit and then whatever the name of your variable is. So you just call this visit on each node. You don't actually have to care what it does. It might be printing it, it might be storing it, it might be, you know, I don't know, computing the square root of the radius of the Earth, or I don't know, whatever it might be doing. We have no idea what it's doing, but you don't actually care. You're just going to call this visit method. This is often called a callback because this node visitor is just an interface. It just tells you what the method should look like, and then people are going to implement the method. And it's called a callback because you're calling back into their code. You're writing code that does stuff, but you don't know what to do with the methods. You're just going to call back to whatever code you've been given to handle that. So it's another way to do elegant designs where you kind of separate out these concerns. Otherwise, you would have to hard code a different breadth first search method for every possible type of thing you want to do. Sometimes you might be printing out just the name of the node just to say what order it was in. Sometimes you might be storing some information about the node as you get to it with a breadth first search, and so you could use a different node visitor for that and so on. So that's what's going on with this lab. Let me think for a second and see if I've missed anything. I don't think I have. I think that's everything. So I'm going to go ahead and stop.